Little bit theoretical. Um, it's I'm going to teach about uh, how to quantize and fine tune the large language models, right? So, have you heard the word called quantization anywhere? Quantization anywhere? No, right? So, quantization is a technique that we use in digital signal processing or digital image processing, whatever computer work here. So, we uh, use the quantization. So, let me explain. Okay. So, first we will see what is a analog signal and a digital signal, right? This is the analog signal time, right? Time, second, the magnitude. Okay? The magnitude will be basically voltage or audio magnitude or whatever, right? So let's say this is the signal, right? This is magnitude versus time. This is a continuous graph. So now, what is mean by digital signal? Analog signal, digital signal. We have heard about this, right? Right. So whatever we process in computer is a digital signal. That's your aware, right? So how we do the digital signal? How we convert the analog signal into a digital signal? So what happens is we basically send this signal through a sampler, right? We call it as sampler or sampling set. So what basically the sampler do is you can imagine like opening and closing the switch, opening and closing that standard interval, right? Every second or every millisecond, every nanosecond, this is open, close, open, close, open, close, right? So that is how frequently it's open and close is sampling frequency, right? Sampling. Based on the sampling frequency, let's say this is 100 seconds. This part is 100 seconds, right? So every second, that means it's close and turn every second, right? What means the signal will be passing through, right? So we will plot the digital signal here. So it will pass through here. This is the thing we are sending it to the switch. The switch will open and close, open and close, open and close. You can imagine like that. Not that's the way it's happening. So, so what is going to happen is here when it's closed, the part of the signal is recorded. When it's closed, that is missed, right? So when it's closed, this part signal is recorded. When it's open, the other part is missed. When you close again, this is going to get recorded. When you open, that part is missed. When you close, again it's going to get recorded. So like that, you are going to get actually signal output. So now what we have done is, this is a continuous time signal. I am talking, you are hearing, it is a continuous time signal, right? So when you break it, even zoom, you can find the value at that point. But in the digital signal, you zoom in. There is a gap. There is no continuous value. So that's why this is continuous. We call it as a discrete signal. There's discrete points, right? From analog to digital conversion. So now we have breakdown into these points, right? Now we have breakdown this continuous signal into small number points. So now these points have a value. So what is the value? So let's say the maximum value is 100, and this value divided into 50, right? 50 to 100 to 90 is there. So here this is 100, right? 100. So now you have this value. So now There are intermediates, maybe 51, 55, 60, 75, like that. These values are there, not continuous. Here, it is continuous. So now what we need to do for the computer to understand, we have to give a certain value. So how many of you learned in O levels in grade 9 in school? The computer understand 1 and 0, right? Binary numbers, right? So now what we need to do is we need to give a binary number to each point. This is 50, this is 100, but these are decimal points, 10 base numbers. So these numbers will not be understood by the computer processor. So we have to give a binary saving number to this guy, right? So now when you are giving a binary number, first decision that we need to make is how many bits that we are going to represent this system. I use a 3-bit microcontroller. So there are 2 to the power 3. Right? So now I'm going to divide this part. Okay, I'm going to say 8 level. Total 100, I'm going to divide it to 8. If it's a 4-bit number, 2 to the power 4, that is going to be 16 levels. 5, 32 levels. Right? So like that, you can divide the level. So let's say I'm going to take a 3-bit number. Representation. So there are 8 levels. So 0 is the first level. And I will say this is the first level. And second level. That should be 8 levels. So now this number is 0, 0, 0. 3 bits representation. 0, 1. This is 0, 1, 0. This is 0, 1, 1. This is 1, 0, 0. This is 1, 0, 1. So this is 1, 1, 0. This is 1. Binary representation of this thing. Clear? So this is called encode. First the sample, then the binary number. So now the quantization will be what? That's the word I asked first, right? Quantization. Now if you see the 50, okay, let's say the 50 is going to be represented by 100 binary number. Is this value? What is this value? That is what you can represent. Because it's in between 100 and 101. Right? So there is no particular binary value can be given to this. What we check is, okay, this value now is close to this one. Right? So the quantized signal will look like now. See, this is the thing. So this value also put it down to this. And I will draw it in another color signal. Right? So we will get to this. Now this is close to this thing. So I will put it to this. This is close to this. I will put it to this. Now you can see the signal that I'm getting it. Something like this, right? It's not the exact signal I am getting. Because the 3-bit is not enough to give the value to represent this thing. Right? So when I come here, this is close to this. Then I will this is this. This is close to this. This 2 comes in here. So like this, right? And here goes to here. Okay. And here, here. So this is the quantized signal that I get. But when you quickly check, this is not that. Right? What we do to increase, to make this happen, so exactly represent that thing, the way is the levels of representation. Right? So when you increase the level of representation, this whole magnitude. Then in that case, these each point is now represented. Right? Again. So now earlier we had a point here. and I put it down because there is no level. So there's an error that I make. That is called as quantization error. Okay. Quantization error. So now, why am I taking this? The middle signal protect. The analog signal. We are counting it, making it a digital signal. So we decided to represent it by this many levels, and we gave the level for each. And we know now what is meant by quantization. So by approximating to the nearest value of the level, the error that we get is quantization error. Is concept clear, right? Now by increasing the quantization level, right, the numbers, the level of representation, what we are getting is we are getting reducing the error. So that means when you reconstruct the signal will be more or less the same, equal, right? So otherwise, when you do a less quantization sampling, which is going to do a wrong thing. I will show some example in this thing, right? So now I will physically show how the quantization will be happening. Right? So now the large language model. We know when we take a text, if we give the word as it is, what is the first step that we have done for a chatbot development? We did a PDF uploading and asking question. So what is the first thing that we have done in that? What is that? Tokenization. Right? So that means you gave a number. Right? You gave each word a number. So that number should be represented in a cell format, a level. So it is a 3-bit number or a 4-bit number or a 2 to the power 5-bit number, right? So we gave cell number value to this thing. So now the thing is, that's the first quantization level. So if you take a neural network, right? So which has a input layer, right? Let's say and another two. Let's say this is the simple neural network. So this is output neurons, these are hidden layer neurons. So we know they are connected to each other because it's called cascaded neural. Like that, it's going to connect. So what we have here, we have weights, and we have weights, and in each nodes we have biases also, right? Weights and biases. The very first class that we have learned. So now these weights are represented in a certain bit form. Our computers, we use 32-bit floating point numbers. 32-bit floating point numbers. Each numbers are represented in 32-bit floating point number. So that means I will show you what is that 32-bit floating point number is. Yes. So this is the 32-bit floating point number. So the first bit, 32-bit, right? 32 bits, 23 bits are here, 8 bits are here, and 1 bit is here. So first bit is the sign, plus or minus, right? And another 8 for the number, positive numbers, right? In the binary. And the rest of the things actually goes to 0.012345. So let's say 100 point something means this is the base part, the full number. This part represents the point form, right? So now this is 32-bit. So we are giving a sign for 1 bit and another 8-bit for the numbers, full numbers, and the another thing for this one. So the range of this 32-bit floating point number is we can represent 10 to the power minus 38 to 10 to the power 38. That is a huge range of numbers can be represented by this 32-bit floating point number. But now the problem is this is 32 bits long. It's a IEEE standard format. It's not the binary converting way, right? It's a little different representation to represent the binary numbers. Okay. So now 32 bit. So now when you are loading these weights and biases and all these points, all are going to be represented initially in 32-bit number. So that means if you take a weight, that weight will be represented with a number in the binary plus the rest of the things are floating point number. That means 0.5324566 something like up to that. So what is the thing is, for example, let's say one bias or one weight is represented as in the binary scale 10.5325789 10 11 like let's say another 10 decimal points numbers are there. 10 point another 10 numbers. So let's say 10.5678910. And another bias number is 10.45678. That's a small difference, right? It's not a big difference. 10 is there and the point numbers are going to be different. The 10 is there in the another way. The point numbers are going to be different. So, but this neural network that we have built up is represented by whatever we have built up to now. The weights and biases are built up upon 32-bit thing. 32-bit, this representation. Each bias, each weight is represented by 32-bit number. So it's a large number, 32 thing. So when it's loaded as a matrix, imagine we can put it as a matrix. All these neural network is going to load the whole bits, 32 bits into the matrix. So when it's do multiplication, it's going to do the 32-bit multiplication. So the computer gets loaded. At the same time, the certain numbers are given to 32-bit representation. The memory is loaded. For example, if you take a neural network, which is having with that we have trained for the character recognition, handwritten character recognition, that is built by 32-bit point, because whenever we run it, typically the computer will do it in 32-bit traditional formatting, each number, right? Each weights and biases. So when we load that model into our thing, let's say that model have 500 MB weights with these 32-bit representation. If we represent the same weights and biases in 16-bit representation or 8-bit representation or 4-bit representation, 4-bit means total is 4, or 2-bit representation, that means 2, the size is going to be reduced a lot. So let's say the initial model that we have trained, for example, is 500 MB, 32-bit. If you come to 4-bit, that model size will be maybe 50 MB or 40 MB size, right? So now what is happening? The model is large, right? So it takes a longer time to load because the memory need to be represented by 32-bit in register. We load the number into a register. Have you learned how embedded system? No, right? So in the computer have registers in the microprocessor, right? So when you load a number, we load it into a register. Another number, we load it into another register. Then we multiply and put it into another register and save it. So that's how each operation is happening in nanosecond. Register means it's a hardware setup like inside a configuration. So now earlier you can load one number in one register. Now when you quantize it, that means reduce the size of bit representation as I showed you right here. So you are going to increase, you can get each point very closely. The error is less. When you reduce the number, the error is going to be really high. So when you having a 32-bit, the error is less because it's a bit representation. You are going to load it into each register and you are going to multiply and put it there back in for one multiplication. But if you have the 4, you can load 8 numbers in one register, another 8 numbers in one register, and you can multiply 8 numbers at the same time and save it in that spot. So that means what is happening? First thing, you are reducing the size of the model. Second, you are increasing the speed of the multiplication. Why? Earlier it multiply one number at a time.
Now the same register can multiply 8 numbers at a time. You are getting it, right? So because the register size is that. So now by doing this, what we are doing is we are reducing the size of the neural network model, right, that we have trained, because we are going to represent it by 4 bits, the same weights and everything. And at the same time, we are going to increase the reduce the computational power. So it will be quickly running faster. So why this is needed? When it's come to large language model, I'm talking about few number of neurons, right? Maybe 10,000, 20,000, 60,000, in thousands. The large language model, 175 billions parameters. 175 billion parameters. That means you can imagine each weight represented by 32 bits is going to be huge computational power. That's why you can't load the ChatGPT into your model at all. Why? Your computer cannot handle that. First of all, the weight is high, it's huge. Second, it cannot process. Then you ask a question, you have to go, you'll be dying by the time you come back. It will still processing because it cannot run that fast. So that is the issue we have with this ChatGPT and big language models. So how we can overcome these stuff? So for example, if you take the ChatGPT is trained on everything. It know law, it know medicine, it know everything, it know you, it know me, everything it knows, right? If you ask any question ChatGPT, it will be able to give an answer. Right or wrong, that's a different story because it's trained based on the scripts provided in the internet. But in certain cases, let's say I want to have a law or AI. So for Sri Lankan lawyers, what they do is they have a team, right? So big lawyer is there and there will be 10, 20 lawyers under him as a trainee or a whatever the training people. So the big lawyer is the name guy. So he is good in winning the cases. So for one case, he will take 10 million rupees. So he pay these 20 people at the bottom. So they do the groundwork. So when the case come, they go, they ask these questions, they go through the books, identify the case, previous cases, draft the case thing and negotiate, give it to him to go and talk. That's what happened mostly, right? So this part happening in the bottom can be done by AI. Based on the knowledge that you have, it's very clear we can do that using AI if we have the law books. When you ask a question, it will go through, iterate, and finally give the answer. That's the future. So, but if you are going to do it with the ChatGPT, it is possible, right? But the problem, you are going to leaking the client case to the GPT. So let's say I'm a client. I did some bad things and I got caught, and the police caught me. Then the police is put me into the jail, and then my lawyer is using ChatGPT to draft the court case. And he is laying location, blah 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 thing. He have done it. These are the law books in Sri Lanka. Draft a case to me, like he said. He will draft the case, and finally, he will win the case for me. I come out, and if I come and ask GPT, who is Lohisan, it will say Lohisan got arrested in this case and everything, and because it knows data is leaked. So that is not a feasible option. So that means we should have a secure model. Secure model. We cannot release the data to any public models available in the internet. So to download the GPT kind of things into our model, it is not possible because it's big. So now what we do is the people started to reduce the parameter size to 7 billion, 8 billion, 13 billion parameters, right? So a neural network built upon 170 billion parameters, more than that 540 billion parameters are there. Based on that, when you are building up a lot of things, the efficiency of the model is going to be really good. But when you are building up an 8 billion parameter, definitely the model performance is going to be less, right? But still, that 13 billion parameter of 8 billion parameter is really heavy to run on a machine. Let's say you are decided to use a 8 billion parameter model to do your case generation or chatbot for your low cases, but still it is heavy to run on the thing. So what we do, we take that model, we do the quantization for under bits. Let's say now it's in 32-bit quantization level. We take the 13 billion parameter large language model, Lava, or whatever the things that there is, Misrael, Lava, Llama. There are many models available in the internet. Go Hugging Face, it's openly available. It's a free source you can download. So that's what we are going to do today, right? So download and you can keep it in the computer. But the problem, when you run again, the computer gets stuck because it cannot run with the GB of memory, CPU, GPU that you have in your local computers. But if you run in the Hugging Face GPU, again you are releasing the data. Hugging Face is getting that data to that model. So they will use that somewhere else, right? So data is everything now. Data is the business, right? Data is the business. If you see this person who walked from some place all around Sri Lanka, there is a Muslim guy, walked around all over Sri Lanka. So he got very popular during these walk. He started with nothing. So when he's a TikToker and YouTuber, right? He's showing the tourist places all around Sri Lanka and walking here and there. And when he go to place by place, his followers started to follow him, right? And they started to give him a support. So when he came to Colombo, there was a huge traffic in this area, Gold Face, because that much of people met him. And he have a huge fan base now, right? That's a that's a business now, right? If you have a followers, then you are a millionaire. You can become a millionaire. Now, what happened recently? Presidential candidates started to meet him, right? So he met Ranil, he met Sajid. I think he will meet Anura too sooner because he have a fan follower. So if this guy say, I'm going to support this person, at least out of that much of fan followers, 20 people of the person listen to this guy. That's a lot of number of votes, right? So data is very important. So this data that he have in his thing, the followers that following him, everything is important in the world right now. In the future, I don't think engineers, doctors going to make much money. Trust me. The people who do social media stuff and everything, they are the people who are going to earn. There is a YouTuber, I don't remember his name. He gifts Ferrari car, big cars as a gift for the competition. What he does is completely YouTube. He earns through YouTube in billions per month. Imagine, like that much of fan followers are there, right? So even Nas Daily, he came to Sri Lanka to promote Sri Lankan tourism. So do you think he just came for free of charge? No way. Our people paid him. He came because of that. Because he have a Nas Daily. After his promotion, a lot of people started to come here. That's how they earn money, right? So these are the things. So this is out of the range of our thing. So now let's say you take a 13 billion parameter model for your chatbot. You cannot load and run it in your machine because your machine do not have that power. So you have to reduce the size and increase the computational power. So what we do is we get the 32-bit weight number represented over here. Quantization. Quantization mean earlier we represent this total thing by 32-bit number. Now I am going to reduce the level of quantization, which 4-bit quantization. I am reducing the number of levels. Earlier, imagine we represented by 2 to the power 32 level. Now I am going to say 2 to the power 4 level, 16 level. So now by under quantization, what is happening is middle numbers here are going to be approximated to top numbers. That means the error is becoming high. So the error is becoming high and the output is going to be quality is going to be reduced because it's we have changed the rate. Complete it's something earlier with 32-bit, but when we are downsizing to 4-bit, we are giving it a different number, approximating to the new file. Right? So therefore, you know how the multiplication happens and the output is decided here, right? In the first class, we have seen. Multiplied by the weights and activation, finally you get the output. You know that. So when you change this weight, the output also get affected. Right? So now what is happening is we are reducing the quality of the large language model. If you ask a question, will give a very detailed, very nice answer. When you give quantize it, after that it's going to give an answer, but it's not going to be appropriate. Right? So that is called quantization. So by quantizing, what is the benefit that we are going to get? We can our
computer. We can even mobile phone app, we can have a large language model in the mobile phone app. For your own large language model, no data is going to get leaked. The same time, it's going to be faster than 32-bit floating point number representation. Two things. But the negative that we are getting is we are using the output quantity. Right? For example, if you ask me joke about Donald Trump, the first 30 million model give a nice joke. But if you ask a quantized model to ask Donald Trump, it might not know who is Donald. The data is missed. So it will give a joke, it will be not at all good. Right? You get it what I think, right? So now we lose the quality, but we achieve size of the model and high speed performance. Two things actually. Now the thing is how we are going to improve the reduced level of accuracy to a good level of accuracy. Any idea? Now you get this how the model quality is reduced, you get it by this, right? By this quantization issues. So now we are going to use that for Sri Lankan law. How we can change that thing? Any idea? That is called fine tuning, right? Fine tuning. So we don't want the model to know about Donald Trump. Who cares? I'm going to build this model for my application. So I'm going to train on my own data. So that means, for example, if you take a Sri Lankan law, it's going to be Sri Lankan law books, right? So I want this model to know only that accurately, right? 100% accurately, it should know about the law books. I don't care about Donald Trump. I don't care about anyone in the world. Only I'm going to use this model for the law books, right? So what I do, I take the scripts, I do the training, that is called as fine tuning, right? You create the scripts and you train your scripts with that model to do a better performance. So that is called fine tuning. When you are training the model from the scratch, it takes billions of dollars, because it's not possible by a normal man. It's cost a lot of GPU power, right? If you are running on a CPU, you cannot finish the training by this life. So you need GPU power. So it's going to take a lot of money for the GPU power. So you cannot afford it. So what we do is we do not train. We do fine tuning. Fine tuning means we can take it this fine tuning in a way. This is not the right to explain, but you can think as it is. Okay. We select couple of weights and we change that one, not the whole the weights, one way, right? Or we keep couple of layers freeze. The weight is freezed. We are not going to touch. At the last layers, we classify change the weights. So a couple of weights are freeze, not going to change. Couple of weights are going to change during the training. So these kind of approach. Or we divide the block into 5 or 6. And we are going to only take one block model, so that neural network, and we are going to do the training for that. So these kind of approaches are taken in fine tuning. There are multiple fine tuning options are there in online, right? So DFQ, QLoRa, LoRa. So there are a lot of options. All are mathematical function. How we do the fine tuning part. So quantization is one thing, which is reducing the size and quality, increasing the performance. But fine tuning makes the quantized model to work better in a certain case. Now, is this concept clear? Right? So this is going to be the future. Why? The data issues. Right? So imagine where are you working? Huh? Yeah. Data entry company. Then you might need this one, data, right? So you have your own model to deal with the data. Right? So medical. For example, I cannot ask any question in US. A person's medical data is released. He can claim against that insurance company billions of dollars. Your medical data belongs to you, right? Nobody can access that, right? That means the insurance company have the access for your medical record. But if your medical record got leaked, he can file thousands of millions of dollars from the insurance company. Insurance company should pay that money. So therefore, this data is very, very private thing.
So now when the insurance company want to add a chatbot or a assistant, AI based assistant to their customers, they cannot go for ChatGPT. They have to have their own model, right? So these are the things that they can do to do that. For example, let me tell a story. So there was an insurance company for in US called Blue Cross Blue Shield. Have you heard about that? Blue Cross Blue Shield, right? So it's a big company. They have millions of billions of dollars. They are having the power to support the presidential campaign also in US. A big company. So they when they get the people to work in, you cannot. They have to go through a security check-in. They cannot take anything inside, right? So they have to go as a person with bare hand with nothing. So in the thing, office laptop is given, computer is given. In that office laptop, you cannot put any pen drive. It's fully secured environment. You cannot get anything out, right? So you have the freedom to access to the internet and everything. So one time, what happened? Uh, but there are a lot of Indians, Sri Lankans are working in that. It's a software, mainly data company, ne? Insurance company. Mean you are managing the patient's data and do the stuff. So they hired a Indian team, like 5 or 6 people for a particular job, right? For a particular project. So what happened? So it's a funny story. So the interview happened in New York, right? So these virtual interview, Skype interview. So there are a lot of firms in US, consultancy firm. What they do is they are recruiters. So they recruit the people instead of Blue Cross Blue Shield. Right? If they are a foreigner, I'm a Sri Lankan, I want to work in a US company. The US company will not take any risk. They will hire the people through the recruiters. They will interview, but that is through the recruiters. That means if the person did any bad thing or anything, that the recruiter is responsible for that thing. So if they are cheating on the visa, the big company will not need to pay anything because they are paying the recruiter. The person is working for the recruiter, but he is working in this office. So it's a setup to cheat the government, right? US government and avoid the risk because they are a big company. If they get caught, they have hired an employee by cheating a visa case or issue, they have to pay billions of dollars as a penalty. But this small company, they just made to pay maybe $10,000 because they are not much making profit making company, right? So they keep these kind of people underneath them. So in New York, they hired a person through a recruiter. They do the interview anyway, right? Because they are going to hire them. So in a Skype interview, a couple of people from New York they attend. They super clever people. So their per day salary is $500. Very high end employees. Very high end employees. They were making a lot of money. Per day salary is 500. You can imagine how much they are going to make, right? So yeah, so 15,000 or $20,000 per month, as I remember, with all the benefit. So I got to know the person through a recruiter. He is a friend of mine. So 5 people got hired for that position. They went to this company, and they were working. They are doing the work and everything. Finally, fine. So when they're doing the maintenance, IT maintenance, what happens now is they got to see 8 a.m. some people remotely logging in to these 5 people computers, right? Right from India, and at the office closing time they are logging off. Right? They are logging in from India and logging off during the work hours. It's not good name because it's an insurance company. You cannot do anything. So then they check these people, inquired them. Finally, they got to know these people didn't perform the interview. They are sitting and the person is giving the voice from side for each. They are syncing up the mouth. It's a virtual interview. So they got hired because of that person who gave the answer. He's with the laptop and answering, reading the answer, right? So, but these people got hired, they don't know anything. So now what happened? They are getting a lot of monthly salary. They set up an office in India. They give the work to that Indian people. Indian people, they do the work. They come and sit and enjoy. Now the problem is they got caught, but they cannot file a case because if the people of that company get to know the clients, this happened in this company, nobody will go for it. And they can sue that company also. So they simply ask them to leave. No court case, nothing. Right? So these are possibilities. Right? So if in that cases, this is the best option. You can use your own private model by quantizing and fine tuning. So now we will go through first the quantization part tutorial. So now the issue here, this quantization may not be feasible for you to run in your computer, right? The first tutorial in that under 40. The reason you need a lot of GPU power and the RAM power to do that thing. So let's see T4 high RAM kela make connect to. You can also make sure is it there for you. So let us run this one. So we are going to download packages, which is a large language model hosted in the GPU, which is called as Hugging Face H4 14th week. You don't have the access? Huh? Capital SIST at 2001. All capital SIST at symbol 2001 SIST management. Huh? So you can do this stuff in Hugging Face also, right? It's a free thing. You can access it. We'll try to run it here. Sometime it might give an error due to these high issues, high RAM issues. But first, before we run these individual codes, I will walk you through the solution. What are the answers looks like and everything. Then we'll try to run. Okay. Sometime it might give an error due to the RAM issues. Google Colab cannot handle the large language model downloading, right? So what we are going to do is we are going to work with today is Hugging Face H4 Cypher 7B beta. That means 7 billion parameters. 7 billion parameters, right? That means total weights and biases add together 7 billion. So you can imagine, like, definitely the computer cannot handle that much. We have 16 GB RAM and everything. So we'll see whether we'll be able to handle it. So first, we are going to work with this thing. So first we need to download all this stuff. So let's connect to the Hugging Face and the relevant transformers and Hugging Face library to download the 7 billion model to our thing. So sometimes the memory also will get stuck. Okay, so installing is fine. It will run because it's not going to take much memory. But after installing, I will go through the solution that I got earlier, right? So then run the only first one. Huh? Then after that, he'll go through the solution. Then after that, he'll come and run it and check it. So now another, this Hugging Face model is represented in B float. That means floating point number of 16 bit, not 32 bit. Already they have quantized it from 32 bit representation to 16 bit quantization. So now it's quantized in the format of 16B. So that's why we call it as B float 16. So if you come down, I'll show you how the B float 16 is. Float B16 means one bit is sign and another 5 bits is for exponent and another 10 bit for mantis, right? So other one is sign. B float means sign. It's also 16 bits. But here we gave one, this is mentioned as wrong, 5 bits. 1, 2, 3, 4, 5, 6, 7, 8 for this part and the remaining for the other thing, right? So 32 bit is this format, 16 bit is this format, 5 given for this number main exponent 1. This is 1 for that to that thing, e to the power 38 minus 38. So here 6 e to the power 8. Here 1 e to the power minus 38. So that's the range. Range is different. That's all. Okay. So let's let it run. So we will go through that thing. So this block is to install whatever the library is required to download the this Sapphire 7B beta model to our Google Scholar. So once you run this code, it will download the whole code over here, right? So all the parameters downloading, the shreds downloading, all the tensors, all the weights and everything is downloaded over here. So let's not run it for now. We'll go to the other thing. So now we downloaded the model. We have used this model somewhere earlier also. Not this model exactly, some other downloaded model in our PDF thing. We asked question, it gave a complete trash answer. You remember, right? We used GPT, but it gave a very nice structured answer. We load the thing and use a local open source large language model, it gave a trash answer. So you know the difference between those two, right? So now we are going to give a role to this guy, okay, saying, okay, messages, your role is system. You are a friendly chatbot, right? And role user, I'm asking, tell me a funny joke about Donald Trump. If that happens, so this is the you are a friendly chatbot is the prompt going to this large language model. And along with my question tokenized, tell me a funny joke about Donald Trump. Get it? Yeah, cool. So then it gives the answer funny joke about Donald Trump and these are the things. So this is the chat context, right? Chat context system. Okay, the system gave the you are a friendly chatbot and I'm giving a funny joke. This is the query that I'm asking to the chatbot. The chatbot should give the answer for me. So for example, you are a friendly chatbot. Tell me a funny joke about Donald Trump. Why did Donald Trump wear sunglasses indoors yesterday? Right? So because he heard that Barack Obama is following him. I don't know this is a joke or not, but this is the joke that we can give. Imagine, okay? So this joke is meant to be, see this, this is the smart thing about this large language model. This joke is meant to be light-hearted and not intended to offend anyone's political beliefs. They have specifically mentioned, I believe, if anything in the large language model training, they have mentioned if you ask if anything political things, put these quotes in the bottom, right? Funny thing. So other thing is shredding. We are going to do the quantization. Now it's 16B floating point numbers quantization level. This is quantized. So we are going to shred it. So one way is this is the whole language model. We are going to break it into pieces. Then we are going to do the quantization individually rather than running the whole language model quantization at a point, right? So this is called as accelerator. And these are the 32 we have discussed how this is represented, right? The original number is 0.12434 and you can see this one is floating point 32, floating point 16, floating point B float 16, how it's represented. You can see 75505 and this is the same number is coming up. So here the floating giving an infinity number. Here it's giving a different number which is completely different than the original number that we have converted, 75,505. Now it's giving us 75,264 after reducing it to B floats. That means we are losing an accuracy here. You are getting it, right? Yeah. So then we come here and we need to do certain work. I will go through that and I'll show the output. Yeah, this is the place that I got trapped yesterday, but there are something. Okay. So you are a friendly chatbot. Tell me a funny joke about large language models. Okay, I'm going to chat it again. Then, yeah, let me see the questions, answers. Okay, so again, I'm checking. So where is this loading your LLM? Let's play and come back. Okay, we'll see how that works. So you can see after quantization, the model performance get reduced in that case. So we'll run and come. I hope the model will work in this RAM capacity. If it works, it's luck. Yesterday I got an error because I don't know, my performance went really bad. So now we are downloading this Hugging Face, all these parameters into our GPU. So let's download all this stuff. So the model that we are going to work is Sapphire 7B beta. Okay, so that's the model which is in the Hugging Face H4. So you can see the disk space is like almost full because the model is very heavy. Is it done for you? Downloading? Done? Not yet. Okay. Joke about large language model. Okay. Is it done? Okay. So can you change this to the large language models? Tell me a funny joke about large language models. Because if we get stuck, we can compare the answers later on with the available stuff. Okay. So we'll try this one. Okay. So what is this one? This is a query with the prompt. You remember, right? In the PDF stuff, okay, answer, you are a PDF assistant. Then we ask a question, it find the token, send it to the GPT and give it. So now we are asking, you are a friendly chatbot. This is the prompt going to that thing. This is my query to the large language model, right? So this is a thing. So this is how it works. Ne? So start of sequence and you are a friendly bot it gets. And this is the prompt, end of sequence. After that user instruction, tell me a large funny joke about large language models. Then the model answer will be given to you. So now we'll run this one. So here you can define the prompt is given as content message, right, then max new tokens 256. I can reduce the number of tokens. Do sample true. Temperature means, what is the temperature we discussed, right? When you change the temperature to maximum, the variation will be high. If you reduce the temperature, the variation will be low. So when you increase the variation of the answer, you might get a wrong answer as well. So it should be in the proper way. So I set the temperature to this thing. So then we will run the model and see how this large language model giving the output, right? The Xavier 7B, B16 flow. But if you would like to learn something in the future and want to perform some work in LLM, this is the one you have to concentrate on. Quantization, fine tuning, right? If you know these two stuff, you can build model for doctors, lawyers, engineers, construction engineer, this engineer, that engineer. Fine tuning means you are going to give all the detail and fine tune based on their knowledge, based on their script, right? So therefore, imagine this is the thing. So you can give the knowledge in two ways. You can give a PDF, upload the knowledge, and you can ask a question, it go through, find out the chunks, and give it to the, it takes time. A lot of tokens are going to be get wasted because 5 chunks mean you are going to send a lot of paragraphs there and you are going to get the answer back. So the token chances are going to be high, right? Or else the token amount going high means the performance also takes time to give the reply, right? But rather than uploading a PDF, you give that PDF knowledge as a fine tuning. Now it knows already. So when you ask the question, it will directly give. You don't want to go through the search and find it, right? So that is the best thing about fine tune. So this is going to be the future. Many people are working on. If you go to Google Scholar, type it out, fine tuning and quantization. Like recently, 2023-24, like there are like thousands of papers are there, right? And they have started companies individually. Each paper is behind a company because they are selling it. They are trying to selling it. Okay, if you want a model, come to us. We'll do it, Kela. So it's going crazy, right? Okay, so this is the output I got. You are a friendly chatbot user. Tell me a funny joke about large language models. Okay, why did the large language model go to the party? To impress everyone with its vocabulary. But unfortunately, it keep repeating the same jokes over and over again, making everyone groan and roll their eyes. The punchline, it had limited sense of humor. So something it gave as a joke. This is a joke it gave, right? Even Donald Trump, when you ask, you can change the prompt here and you can ask the Donald Trump joke. This is for B float stuff. Is that clear? Did you get it? Yeah. Okay. Cool. Yeah, it can be. What is the one you for you? Okay. Okay. It can happen because it's LLM. Anyone else? What is your one? The same? Different. Okay. Your one? Okay, okay. Then you can share with him. So now, before we go into the quantization strategies, there is another trick that we can employ to reduce the necessary virtual RAM for loading our model with shredding. We are essentially splitting our model up into small pieces, shreds. So that's what we are going to do to increase. So we are going to share it into 1 GB, shredded our model into pieces of 1 GB. So to do that, you have to run this thing. Why? Because the problem, our RAM amount will not be enough in certain cases. So maybe, uh, yeah, we'll see. If this is not working, we will change that thing to 1 GB and we will see if the VRAM is not going to work because we need a lot of memory. Maybe I can say match shredded size to 2 GB. We'll see. First, we'll try with 4 GB. So this is to make sure we are running faster in our limited RAM memory because we have 16 GB. That is not enough at all. So, but it worked earlier. I don't know what happened yesterday to me. Earlier, when we are building this one, it worked properly. And these days, there are Medium articles. Medium, have you read something called Medium? Medium is the people who contribute for the open source knowledge mostly. It's paid version also there. Enough, free is enough. If you go to Medium articles, you can know a lot about these quantization. So what they do, they work on a particular aspects, and the researchers come and write in the public about their findings and everything. It's interesting and very well drafted in certain very nice language, easy to understand. I learned about quantization through that Medium articles, right? So it's happening. So now there are two projects running under me. So one is Sinhala LLM. So we don't have a LLM. So large language model. So what we are doing is we are training a single LLM. But the problem, training a single LLM will cost millions of dollars for you. So what we can do, what we are doing is we are taking a 13 billion parameter model, quantizing it to 16B floating point number, B16. Then we are fine tuning with singular scripts, right? Fine tuning with the singular scripts, not training. For fine tuning itself, we need around 30 lakhs money. But one company said they will support us. We'll see how it goes. So once the single LLM is fine tuned, then you can use it for particular aspects, right? For example, let's say a government organization want a single and Tamil chatbot. Simply you can integrate this one based on the knowledge base. You have to fine tune again based on the company knowledge base, but you can use it for a particular index. So it's a small try I'm doing to see how that works. 3 students are working on it. So the ultimate goal of that project is to navigate a robot using singular commands. So that means you say, go to the kitchen and pick this object in single, complete single. The bot will understand and navigate and pick the bot and come. So that is the option. I went to China. China, there is a bot. That's why I did take 3 weeks courses. So there is a bot to deliver food in the hotels. So the Uber drivers come. There is a hotel robot. So they come and press this thing and keep the food inside the robot. It will go to the room and deliver. So I have a video. I'll show it to you. It's crazy. It communicates with the lift. It set the speed and set the floor, go to the floor and go to the particular room. And it's a robot. And how can you imagine like how it hold the person inside the room out? Because it cannot shout because it's a soundproof room, big doors. You cannot see whatever is taken in the corridor. The people who are talking in the corridor cannot be heard inside the room. It's fully sealed, new sealed. Any idea how the robot called the person? So because he ordered some food, Not Uber, some person came and put the food inside the robot, set the room number, and the robot go towards the lift, and the lift came and set the room number. Setting means automate all wireless communication, right? And the lift took the lift to that robot to that place. Robot came out, navigate to that door, and it's standing outside the door. I was waiting how it's going to call. It's called the room telephone. There's a telephone inside the room. It's ring that telephone. And when they picked up, it told something. I'm waiting outside or something. Then they came and took it out. It was super amazing. So I'll show a video at the end of this class. Okay, so we just shredded that model into pieces now because that will be easier for us to work with the virtual RAM. So you can see the disk space now and the RAM space. 2.8 GB RAM is used. Disk is almost, see GPU RAM, 12.7 is used. Never you have seen this kind of statistics in the past because we didn't use that much earlier, right? So let's see. Now we have seen quantization, dequantization. Let's run this one. Accelerator, and we are giving certain 4-bit loading in 4-bit quantization format. Earlier it was B float 16. Now we are going to quantize in 4-bit quantization. Hopefully this will run. We'll see. Yesterday it gave me an error. Today we'll see giving an error. So the thing is, some modules are dispatched on CPU on the disk. Make sure you have enough GPU RAM. So that's the issue. We don't have enough GPU RAM. It's giving an issue. But the same model earlier worked with me without any issues. But this GPU RAM is the issue now. How to reduce that? Either one way we can do is we can purchase this Google Colab, paying we can get more RAM space, right? That we can run it. But this is the code. It ran, it worked earlier, right? So you can try it. So we'll keep this one and we'll go to the next thing. So now we earlier the 16-bit is loaded and we saw the joke it gave, right? So now we are going to load the 4-bit and we are checking the thing with the same thing. So yeah, the pipe is not defined. The joke, I cannot get it now due to this issue, but comparatively to the joke it gave earlier, it gave a very bad answer. It's a one-line answer it gave. Why the chatbot large language model go to a party? Then it gave to have a funny chat. That's the output it gave earlier here, right? So it's the output quality is reduced in this thing. So we will not run this one. We will go to this to the other beta GPTQ, and there are much more techniques like how to say in the quantization. So this is one way. Quantization meaning is reducing the bit sizes. But how to reduce the bit sizes by keeping the certain accuracy? Many people have published papers, right? Still, it's not coming to the market. One is GPTQ, right? That is one model. Other one is GGUF, right? Other model is AWQ, right? So this activation aware weight quantization. And other model is known as, yeah, those are the 3 things in this tutorial. Activation aware weight quantization, and GGUF means it's another way of doing the quantization of the model. And GPTQ means it's another way. GPTQ is a post-training pre-quantization. So that means before you do the fine-tuning, you do the quantization. So some sort of an approach, okay? So now we do the thing in here. So you can see the answer is completely different. Why did the large language model go to the party? You can see to make some small talk. That's all. Earlier with 16-bit B float, we got the answer. It's in a little bit elaborative way. You can see. But to impress everyone with its vocabulary, but unfortunately it keep repeating the same jokes. See the answer. So when you quantized it, you are reducing the quality of the output, which is giving Tell me a funny joke about the large language models. Why did the large language model go to a party? To make some small talk. That's all. Right? Simple. Because why? We reduce the quality of that thing. Right? And another approach is GPTQ. So we are going to do the GPTQ based quantization for 4-bit. So here, once it's done, you can see why did the large language model go to a party? To impress everyone with the vocabulary. It kept the, see, but unfortunately it kept repeating same jokes, so making everyone go wrong there. The party goes soon realized that the large language model was more of party proper than a party animal. Something it gave, but better than the previous one. GGUF is better than the GPTQ way of quantization. So these are models, fully mathematics, right? If you read a paper, how they keep the weight, it's full of mathematics algorithms. So they use these algorithms to do the quantization. So let's try it out after checking these answers, whether it works or not. And AWQ is activation aware quantization. That's another way. This is more appropriate for the fine tuning task, right? Activation aware quantization. So if you ask the same joke, here you can see, tell me a funny joke about the large language models. It says, to why did the large language model go to a party? To network and expand its vocabulary. Why did the large language model blush? Because it's overheaded another model saying it was a little too wordy. Why did it give lot of words, lot of jokes? See, lot of jokes. So that's the difference. The idea of this tutorial is to show an idea. The quantization reduces differently the accuracy. 16B float is giving something. You take the 16B float, you use GPTQ, GGUF, and AWQ, activation aware quantization. They are differently giving answers because you are changing the weights in a different manner, right? So that is the main purpose. The second one tutorial is this one, fine tuning. Right? If you open up this fine tuning thing, save this one. Let's load this one. We'll see. Okay. Okay. Did you open this one? Yeah. What we are going to do here is we are getting the quantized model and we have 4-bit quantized model and we are going to do a fine tuning. Okay. We are going to do a fine tuning. Earlier we worked with 16-bit 16B float quantization, quantized model, and we downside it to 4-bit using different thing. So you have seen the answers are given different format, the quality when reduced. So to overcome that, what we do for a particular task, we take the model and we do the fine tuning. So that's what this celebrates. So I will walk you through before we run. This will work in the typical format. Usually this gives manage sessions. Yeah. We will run and go. Okay, first we will load all these things. This is 4-bit quantized model, but it's going to be 20 billion parameters. Another model. Okay. It's called GPT Neox 20 billion. Earlier we did this with 7 billion parameters. So this is going to be close to 40 GB, the size of the model. Now what they do is basically the quantization also takes a lot of time and memory. So in the Hugging Face, they have the same model with B632, B16 float, 4-bit, 8-bit and 4-bit. They have that already. So you can load it as it is without doing the quantization. So right now what we are doing is from the Hugging Face, we are downloading the 20 billion parameters with 4-bit quantized level. So we enable the 4-bit through here, NF4, right? So that's what we are doing. Okay. So let's download the, it's an error happened, but it's won't cause much issues, I believe. Let it download, it will take a while. The second block, go to the restroom. This model is little larger because it's 20 billion parameters. And it can be downloaded in all the format, 4-bit, 8-bit, 16-bit, 6B2. So it's easy for us to directly download without doing the quantization. I thought of conducting the lectures in online and from China. So after go there only I realized they don't have anything. You can't access to chat WhatsApp, you can't access to Google, you can't access to Zoom. Nothing is working. So they have completely isolated from the world. So you have to use VPN. So the VPN will work for couple of minutes, then they identify and they block that VPN immediately. So the Zoom calls only can uh, so you just ignore that warning message. 5 minutes, 6 minutes, the Zoom will call will be ended. It was very hard time I faced. So a lot of pending work here because I thought I can do the work from there and I took everything and went there. Even Google Colab will not work. Can you imagine? Nothing. They completely block the Google services. YouTube, WhatsApp, Instagram, and Google app, Google Map is completely not working there. It cannot work. So, but their development is amazing. You can't even believe how much they have developed. It's super amazing place. Nobody knows English. Again, they are like completely out from that place. They don't know English. Nobody can talk English. So I lived for a couple of weeks with Google Translate. Right? You can ask how I use the Google Translate without any other option. I subscribe for the roaming, 50 GB roaming data. So with the roaming, they allow. But the roaming speed is limited. So you can have WhatsApp, you can have Google in the phone, but when you put it to the hotspot in the computer and try to access it, you can't access Zoom. So the speed is very less. So when you send a message, it will delivered after maybe 2-3 minutes, not immediate. So roaming is possible, but still it's take a long time. So you go to shop and take a Google Translate, type and wait until it's translated, and you show that guy. Then he understands it's in Chinese, and they have an app. They talk in Chinese. It will be translated in English. So that's how all the communications were done. So for 2 weeks, I suffered a lot because I initially thought I can work from there. That's why I went there. But finally, 2 weeks I couldn't do anything. Just attend their seminar and went to the workshops and came back. Good exposure and experience. So in 1971, the economy is really bad. They were comparing their economy with US economy. 1971. Every 5 years there was a chart how the US economy grown and their economy grown. Their economic growth is exponential. Now their economy GDP is equivalent to the US GDP. Equal, more or less equal. But the problem that they have is the population. The per capita GDP is less. That's the issue. But the total GDP is equivalent to US GDP. You can imagine, right? So that's crazy growth. And not only on that, they have talked about the scholarly article citations and stuff, Google citations. So earlier they said, okay, this many people in US got more than 50,000 citations. In China, nothing in 1970s. Then like that, now they have equal a number of people have 50,000 of citation compared to the US people. So it's a growth comparing to the US. Like it was amazing. The presentation I have, I can share it with you. Without knowing English, even the professors doesn't know how to talk English. All the lectures goes on Chinese. But their growth is definitely in next 20-30 years, if they grow like that, they will be the best in the world. Everyone works. Nice people. Means hospitality is there. US, if you go to US, they don't like that you are coming. Chinese, they greeted us very nicely and very nice people. They have very good quality product in their market. They only ship us the bad products. But cannot live there. Food is what you get here as a Chinese food is not the Chinese food that you get there. It's completely different. And for 3 days, I enjoyed the food, different. Okay, wow, like then you can't eat that forever. So after 3 days, oh my goodness, when I'm going to Sri Lanka, that's the thing. Okay, now we have downloaded the model. You can see out of 100 GB, 72 GB space given by 78 GB given by Google Scholar. Almost we have still 72. That's very large, but that's okay. I hope that will be enough. So then we will prepare the model for the training, right? So now we'll prepare the model for the training, and the trainable parameters 0, all parameters 0, and we set all these stuff to their thing, and we are going to define the print trainable parameters. And from PFT import, so we don't want to go here. So I'll show you, as I told earlier, when we are doing the fine tuning, we are not going to train the whole model. We are going to train a selected certain number of weights, right? It can be randomly selected. Okay, we can define the layers of weights also. There are a lot of models. So here we have randomly selected. So you can see the trainable parameters are 8650752. So when we are training, only this much of parameters are going to get changed out of this many parameters, right? So the trainable is 0.08% of the total parameters. You are getting it, right? So because if you try to train the whole parameters, you cannot do here. You need GPU, and the GPU in the computer will not work. You have to hire RTX 6090, 20 GB, 5 of them to do the training, full training, even though that is not enough. Sometimes it gets stuck. So it will cost per minute $0.6. 1 minute training, $0.6. So it will take days or months to do the training from the scratch. So you can imagine the GPU cost. So, and also you are not sure after the training whether the model will work better or not. You don't know. Then you have to test the model. If it doesn't work, the whole thing is waste for you. So you have to start again the training. So the fine tuning is better because the model is already trained in certain aspects. Now it's in English, right? We are going to train this many parameters from this model for our particular task. So the task is this one, right? So we have codes given by certain people. Be yourself. Everyone is already taken. Oscar Wilde is given that code. I'm selfish, impatient, and little insecure. I make mistake. I'm out of. So this is by this person. Albert Einstein. Two things are infinite: the universe and human stupidity. And I'm not sure. Like that, they have given the codes. The person versus the code is the data set that we are going to train, right? So there are a lot more. I think they're like you can see how many things. So like there are totally 2,510 rows of codes are there, which is provided by different people, right? So this is the material that I'm going to use for the training. So that means if you ask any question to this model after fine tuning, it should be able to answer regarding the codes 100% correctly, or certain 90% correctly. 100% you cannot achieve. Or else, if it is not enough, then you have to train it again with much number of parameters. Training also is an experiment. You take a less number, then you do the training, not fine tuning, not good enough. So little increase the parameters, do the fine tuning, not enough. Or increase the data set and do the fine tuning, not enough. So it's a trial and error way. So the same kind of approach that we are using for the singular text. Taking a singular text and this one, and we are fine tuning, right? So now we will download the data sets to our platform here by executing this code. Okay, I downloaded. So now we are going to do the train. Okay, training means the fine tuning by clicking this task. I hope this will run without any issues. Can you run? How many GBs left in your one? For me, 6.14. For you? Same? So we'll see. We'll see. So you are getting the concept of fine tuning, right? Right. There are couple of ways. This is fine tuning of a large language model. When it's come to a model, which is an image classification model, right? So what we can do is we cannot do the fine tuning. There we do the transfer learning approach. Transfer learning approach means that I said you freeze all the weights and take couple of layers at the bottom, like last 2 3 layers, and you train all the weights in that layer. That is called as transfer learning. Okay, you take the model and you make sure during the learning process these couple of weights in these certain layers are thing. Another thing is a common way that happens in the AI world to reduce the weight size. You train the model weight. So why do you need to train? So there is an issue. So the hand character recognition, it works fast in your computer, right? But why we need to reduce the size? We need to reduce edge device. Means let's say you are going to use it in a mobile phone. So you use the train model in the mobile phone app where you take a photo of that handwritten characters. It should tell what are the characters over there. With the train model, you cannot run it over there. Why? The model size is bigger. So you need to reduce the size of the model and improve the accuracy. So what we do is we can do the quantization and we can do the transfer learning approach again to fine tune the model. But mostly in that approaches, we also do the pruning. We call this pruning. Pruning means we remove this branch completely. We set certain ways which are not much contributing for the decision making. There are this many parameters, but certain weights are very minimal contribution for this decision making. Like multiplication is a very small number. So we identify the small numbers and make it to zero. So that is called as pruning. By making it zero, what is happening? You are reducing the size of the thing. The multiplication with zero number is very fast. Then multiplication with two numbers in the register, right? Zero with something is zero. So it knows. So we set this to that is called pruning. So that is also implemented in the large language in the AI neural networks. So that's we have trained it now. So now after the training, because it's we ran only for 10 epochs. So if you want to do it for a little more epochs, you can step it out. Right? I just ran for 10, but 10 is not enough. Right? So then I will save the model as we did it earlier and get the thing. And I'm going to ask something about Elon Musk. Okay, let's ask about Elon Musk now. So I just text is Elon Musk and device CUDA means I'm loading this thing because GPU is needed for that part. So let's see what is giving for Elon Musk. The output should give something. If the Elon Musk said something in that thing, it should get it and give it to me. So there are a lot of data sets available. Uh, Elon Musk is the founder of Tesla, SpaceX, and Boring Company. It gave, but let's say Albert Einstein. Einstein. We'll go to the data set. I'll take this guy. Okay, Chuck. Chuck. Uh, something. Okay, let's run and see. Chuck Palahniuk. So it's a large language model. Anyway, it should know about Elon Musk because the data is there in the internet. It's already trained with that data. But we quantized and we lose certain information. Now we are fine tuning with the codes. So it should be really good in answering with the codes. So Elon Musk, I think in this thing, Elon Musk code is not established. So that's why it's giving Elon Musk is a owner of Tesla and blah blah thing. So but this guy's code is there. Okay. Chuck Palahniuk's novel Fight Club was adapted into film by director David F. What is this? Today's sort of day where you are doing. Okay, you see. Text. We'll ask what is the quote of this thing. I'm not a writer, I'm a reader. Is there anything given by him? There are a lot of places he gave me. Maybe we'll ask Albert Einstein. So this is a training way. You can see this is the quote, this is the author, and we are giving a tags like this. So we have to prepare the whole data set for the fine tuning in this manner. So what we are doing is that to collect the singular data and text and everything, we are doing these tasks these days. It's take a lot of time, but we'll see how it works. I'm not still sure whether it will work or not. So it's foundation of the general theory of relativity, the collected papers of Albert. It's saying something, but still it's not related to the code much, right? So that means you can go there and you can increase the epochs numbers and everything, and we can fine tune that step. So this is the way that we do a fine tuning in a particular task steps. So you load the model, quantize it, and take the quantized model, set the parameters, which percentage that you want to fine tune. Then you take the test and run the training for that parameters. After that, it should be able to perform superior in that text only. I just ran for text for the demonstration, but if you run for many, then definitely it will be able to say, you can see the losses, uh, runtime is this much, sample to a second, okay, train total flows, okay, train losses 2 pi in epoch, so 2.24, it's lot, it's a lot of loss, right? So you can see, and maybe we can ask some more things and see. Einstein quote. Let's run and see. So this is how the fine tuning is working in that way, but it's not an easy task. But if you learn something, want to learn in the future, this is the one it's going to be in the lessons in the future. So because in the AI, we are not going to learn anymore about the traditional AI. Whatever we learned about object detection, many other stuffs are going to vanish actually. So the LLM reliability is little less now, because if you ask about, if you train a object detection model, send an image and ask the objects what are the objects over there, it will definitely identify the objects in the image, right? Let's say chairs, tables, and whatever the things. Then maybe after next day, tomorrow, you upload the same image to the YOLO V5 or YOLO models, ask the objects to identify. Definitely, it will identify the same objects identified yesterday, right? That is the training model. But in the large language model, generative AI, so you ask the model to identify the objects. You don't do any training, upload an image to the ChatGPT and ask what are the objects over there. It will identify the objects. Tomorrow you come and ask the same model to identify the objects. It might miss some objects, or it might identify more objects than yesterday. So that means the consistency issue is there in object detection recognition. So where it will be a problem, you are driving a self-driving car, running on a generative AI, done then, right? So that is the issue. So non-critical application, generative AI is okay up to the date now. But for critical application, you cannot completely rely on ChatGPT or any other generative AI up to this state. But this is evolving. This is evolving, right? So we need to adapt. See, the Albert Einstein quote: "The most beautiful thing we can experience is the mysterious. Is it is the source of all something Kela it gave." I don't know whether Albert Einstein has said it or not. There are a lot of quotes with Albert Einstein here. There are only two ways to live your life. One thing is like that, like that. So you can ask and see. It's only 10 epochs. So it will be, the answer will be given to you. It will say, okay, then it's fine. It fine tuned. See, there is some answer, but it's not enough. So we have to do that part. So other thing is, in China, what I learned, one more thing is they don't have a plan for their government plan every 5 years, not for 30 years. For there is a plan that is goal. They keep it as a goal, but the plan is made every 5 years. So that means they say if you make a plan for AI for 20 years, right? 20 years action plan for AI, you think, okay, I will teach the kid generative AI, machine learning, all support vector machine based things and everything. When I teach, I will teach and I'll bring the kid by 20 years. After 20 years, the kid will be learning like that. ChatGPT comes, all the thing you teach, one API call is done. So your 20-year action plan is a waste. So they always say, don't make plans for long term because the system will mature faster. At that time, one technique is old. Generative AI after 20 years might be an old technique. But our people are working towards 20 years to achieve that old technique. You are getting it, right? So make short-term plans for technology. That's their another approach. They have succeeded. So they are generating a lot more energy in the morning times due to the solar panels and everything installed in the thing. They are trying to achieve 2060 carbon neutral. That means zero carbon emission from cars or anything. 2060. So there are a lot of battery vehicles now also. So there are carbon neutral policies on 2060. So they installed solar panels, a lot of solar panels. They are generating a lot of power in the morning. So they can't save it anywhere. So what they are doing is battery banks. But the battery bank issue is uh, it cannot be used for more years, right? 3 years, 5 years. So the capital cost is high. You can save the energy and dispatch in the night time. But the capital cost is really high. So now what they are trying to do is saving the energy in hydrogen generation. So the excess energy will be used to generate hydrogen, and the hydrogen is saved in a tank. Then you ship that hydrogen to other countries. But still, the cost of making that hydrogen using electricity is very high, very high. So they said Sri Lanka should take some action, but don't make action for 20 years. So, like, keep an action because this technology will mature after certain time only. Once it matured, you can buy the hydrogen for very cheap cost, right? So they are super planning structure, and I was amazed by their performance in the industry. But now they are facing a trouble due to US, right? The US started to ban many things and they started to stop the trading in many aspects with China, right? So because it makes sense because their cities are bigger and beautiful than US cities. I was surprised. High rises building and like superb infrastructure is built in China in certain cities, not in all the places, but they are doing it for all the China. They are building it up. And they said they generate 1 million graduates, engineers per year. 1 million engineers per year. So they don't care much about arts and stuff. I don't think so. So their engineering graduates are the main for them. The engineer gets more salary than doctors in China. So they value that engineering a lot over there. So yeah, in our cases, it's completely different. Engineers get not much salary. The doctors get comparatively good salary. And yeah, I'm talking about government scale. Huh? Private engineers get more salary than doctors. Yeah, that's the thing. So the concept today is understood, right? Quantization and the fine tuning. Unfortunately, I couldn't do the quantization due to the memory issue. Luckily, we did the fine tuning part. So the concept is the same thing, right? If you can run that code, if you have a higher VRAM, so what you can do is you can download the code. If you have 32 GB RAM and maybe 16 GB of GPU, you can run it in your local machine, the same code. Go, file, and you can download this thing. Save, or download, and download IPYNB. Right? Once you download, it will download as a same thing, download as a Python file. You can open in your local Python and run the code, it will work. Okay. So yeah, that's how I implemented this one in my local machine. Then when I uploaded to Google Colab, it didn't work. Right. So yeah, it ran in my local machine. So that's all for today. So next week we have, I believe, the poster detection. That's a good one. We'll learn about that poster detection. Week after that is forecasting or something. I believe AI, music and arts, then industrial application. 18th week. Yeah. Any questions? All good? You have to make the data in a structured format as this question and answer, question and answer. So let's say uh, you you have a question, create a question and answer, create a question and answer. So out of that PDF, you have to think about the potential questions that a client can ask, and you put the answer. Question, singular answer, singular question, singular answer. That's what we are doing now, right? Then we fine tune based on that question and answer session. So then it will be fine tuned based on the question and answer. So it know the context for what question, what answer should be given. It will learn automatically. It will not give the same answer, but it will learn to answer in a different manner. Right? So that's how we are doing the fine tune. Right? So that is the way you have to do that. Structure the data into a question and answer format. Right? No, not needed at all. Not needed at all. So if you have a PDF document, 1,000 pages, you write a code using a natural language processing and generative AI that you are using now to make 10,000 or 20,000 or 1 lakh question and answers out of this PDF. Then you have to check whether those are correct or wrong, right? Then you do the training, fine tune. Even the training is happening in the day, the structured data. So why Gemini cannot achieve a very good accuracy compared to GPT? Because the way of structuring the data is different in GPT. Same training, same billion more or less parameters are the same model. Everything is more or less same. But the data structure is different for GPT. That's the key that they have. How they have structured the data for the training. It's not an easy work. It takes time. It's take long time. So yeah, we'll see how that works. We are approaching in several ways. Take a book, say library, and making these data structuring format and everything. We'll see how that works. It can be automated. You don't want to do one by one. So you can have a PDF and you can do it by a Python code. That is possible. So that's the way. Even if you take a low book, you have to structure the data first, then you have to fine tune. That's the thing. But this fine tuning is a small normal demo, but there are many approaches. We are only fine tuning 0.086 parameters. That is not at all enough. You have to increase the parameters, increase the data size. Then the fine tune will be there. So then it will answer all the questions. If I ask Elon Musk is the owner of something, it gave me. But it will be correct in codes. Right? It gave the code here. The most beautiful thing we can explain is mysterious or something like that. Yeah. So that's how we have to do, but it's not an easy work. It should be a huge task force. India have generated a Indian AI for Bharat, a task force team by government. They are doing these Hindi language models. They have released a Hindi language model. That is good. That is good. But there are thousands or 10,000s of people are working there to collect the data, to train and everything. Government is supporting in AI domain. So our government, I don't think so. We don't have money. So as a citizen of this country, we are doing something in the undergraduate. But the outcome will be a proof of concept. We cannot build a singular language model, answer all the question in singular. No way. But this approach can be followed to do that task in a bigger scale. So we are giving the proof of concept. Okay, we have done this. It worked for this aspect. If you do this way, this will be, we can create a model for our country. Sponsoring that thing or not, it's their problem, government problem. So as an academic, it's our duty to do something to do that thing. As I said, we have built up a tourism app. We went and demonstrated, but nothing worked. They are not interested. So we are trying the best, but government support is very minimum. So after certain time, everyone get fed up and they only teach and do their work. So still, I'm young. I'm doing this stuff. I don't know when I will get fed up with this system and keep quiet and do my work. It'll be sooner, I believe. So doing a lot of stuff, we'll see. Yeah. Yeah, that's all for today. Ah,